Welcome back to Codex. Our speaker today is XY Han, who's a PhD student at Cornell under the supervision of Adrian Lewis. XY thinks about fundamental problems in non-smooth optimization, artificial intelligence, and high-dimensional statistics. Today, he will present some recent work on the neural collapse phenomenon in deep learning. Take it away.
Okay, hi. Right, so I'm XY. I'm at Cornell, and this is actually a work that I started before I came to Cornell with Verdun Papian and David Donahoe. I looked at the past talks at Codex, and it seems like, well, this is an audience who will know this frame structure that I'll talk about and come up. So it's an ideal audience for this talk, and I look forward to sharing it. So neural collapse. This is based on a paper that was published by Verdun, myself, and Dave in September 2020. And here they are, the other two. And it's also, we have a follow-up that will be coming soon, hopefully. And Alan Kipnis will be joining us for that one because it has he's an information theorist, and that has a more information theory spin to it. So to set the landscape a bit, we're all aware to some extent that deep nets have caused a shift in the field in terms of what science thinks automation can do, even compared from 10 years ago. And much of this was in fact inspired by the performance on ImageNet, object detection, cars, natural language processing, text generation, translation, and of course, AlphaGo and such. So AI has really come to the foreground of what we've been aware of. And another shift, which is more distinct to especially statisticians, is that prediction has become the focus of everyone's attention. Whether you win a contest, what these contests can be about has very much been the goal now, rather than say traditionally where people tend to think about, say, inference modeling, hypothesis testing, at least from those from a statistical background. Remember where prediction was not as prominent as was today. And of course, because of this contest-driven, prediction-driven paradigm, we do see this very rapid drop of performance, which is most obvious, again, in the ImageNet classification setting, where we see these drops. But this one is the big one that started this whole deep learning revolution. But ever since then, we still see this drop, and what people consider to be human level performance is around 5%. And around 2015, we reach what people tend to call superhuman performance in at least the image classification task. And the bar has just been dropping since then. And part of this whole paradigm is people try to outcompete each other in terms of these percentage points of performance. And central to how this performance is achieved behind all this is these deep nets. There's so many architectures, there's thousands of teams just working to create them. Behind every deep net, there's these narratives of, oh, my deep net works because like it stops internal covariant shift because I added this batch norm feature and such. And because, and you make these things deeper, and because there's so much variety and no lack of heuristic explanation, but definitely a lack of theoretical explanations, for someone, say, from theoretical statistics, you might think, oh, like there's so much noise in this, there must be so much particularities. Is there any way to mathematically analyze this? Is there any way to even find some structure that we can model across all data sets, all networks? What can be done? And that's really the focus of this talk, which is what we found is if you just take this more experimental gradual approach, you'll see that there is a common mathematical structure. an equiangular tight frame, although like given this audience, I'm gonna add a caveat to that soon. That does emerge, especially in the last layer of the deepnet. And in terms of theory, we can actually see why this structure would in fact be the optimal preferred structure were you doing the classification task. And what is the common training paradigm that we are talking about? When training deep nets, there's this new idea, of course, of interpolation. And what that actually means is, say you train for a lot of epochs, and epochs we mean just going through the entire data set through one time using stochastic gradient descent, but among other possible algorithms. And what people nowadays tend to do is, even when during training you fit the entire training set, so the deepnet is now able to learn all your training set perfectly, it effectively memorized it. There's a smooth loss called the cross entropy loss, which I'll show the closed form later, that you're still driving down. And what people found is this actually does, even though your training data set has been perfectly memorized, the continual minimization of the cross entropy loss towards zero still has performance benefits. There's an alternative school of thought that's early stopping. That could be explained through, say, regularization, but that's a different school of thought that won't touch upon today. And the reason that we could do this, the first one, which is memorize and just keep training, is because networks are massively over parameterized. You have so many layers, and within each layer, there's a few hundred sometimes parameters in itself. And once you hit interpolation and you keep training, that's the phase we focus on today, which is called the terminal phase of training. And getting slightly more into the technical details now, we consider the classification problem. And within the classification problem, there's these standard benchmarks, for example, MNIST, Fashion MNIST, SVH, and CFAR with 10 classes, CFAR 100 with 100 classes, and ImageNet, of the famous one with 1,000 classes. You have images, so these X are images from each class C, and there's I of them. Within each class, they're indexed by I. And what we see in a deep net, what happens is you first have these preliminary layers. And then after going through, say, the first 100 layers, the last layer is what we call A. The output in terms of the activations of the last layer is what we call H. And this is a high dimensional feature, say like a few thousand, a few hundred dimensional. And then on this H, there's a linear classifier. And so another linear layer, basically. And on this, for each class, so this linear classifier multiplies each activation from the last layer deepnet, and it gives you what's usually called a score. So this inner product here. And among all these scores, which occasionally you also take a softmax probability of to get them renormalized to 0, 1. But among all these scores, you then take the largest one, and that's your deepnet performance. And what we'll be focusing on is that layer right before the linear classifier of a deepnet. And we shall call that H here. And now that we introduce this notation, we can introduce the law of what we mean by loss and error. So here, the error is just the percentage when so C hat here is if you remember, the prediction of the network when you take the argmax. So here, the error is when the percentage of the time, because we're taking an average, where the deepnet prediction is wrong on the training set. And the loss is this so P is the sigmoid function effectively on this linear, right, this guy. So you take the X and you renormalize it across all these inner products, and this is the sum of all of the average of all of these is what's typically called the cross entropy loss. And what happens is when you memorize your training data set, this becomes 0. But this will never be 0 exactly. So you just keep driving this down. People have shown that this actually does give performance benefits. So it is a paradigm that's practiced in deepnet training. Again, there is an alternative school of thought, early stopping, not going to touch on that today. So then, how can we start examining this? Well, we're gonna have to define some terms. And remember, what we care about is these last layer activations of a deepnet, and we'll aggregate some statistics from it, such as the mean of these last layer activations. So we have these 100-dimensional activations on the last layer, and we take their average, which is what we call MUGI, their global average, within each class of their training set. We also take a class mean, so we average over the index I of each class, but we don't within each class, but we don't actually average over C, the number of classes. And then you also see these canonical summary statistics of variation from statistics, such as the within class covariance, which is interclass variation. You see, you subtract the class mean, you take the activation, you could subtract its associated class mean, and I'll visualize this soon. And of course, there's also the between class covariance, or the intra-class covariance, that kind of talks about not about how activations vary within the class, but how class means how separated they are from each other. So visualizing this, we have this, and you start seeing hints of this tight frame that we start talking about. So here we have the classifiers. So these are the W vectors that will eventually multiply the 100, say, dimensional activations. And these are features. So these are the actual representations of each image after passing through the first 100 layers, but not, say, the last linear layer. There's a class mean. So if you aggregate over all these individual features, you have these class means. And you would expect that to get this high score, you want the classifier and the mean to be approximately the same, right? And so this is what we call the within class covariance. So within each class, how much jitter is there within each class, right? This is what we call sigma W. And of course, there's between class covariance, which is these are the means, how separated they are from each other. And from this picture, you kind of get where we're trying to go here, which is we'll show that as you train a deepnet, empirically, you'll actually expect these to become maximally separated and the noise to go to 0. And that reaches what is a high dimensional variant of the equiangular tight frame. So again, what we show, the empirically will show first these 4 properties. The first one is called variability collapse, which is neural collapse 1, which is the within class covariance. You see all these features will eventually go to 0. They'll shrink, shrink, shrink until you get this perfect no within class covariance, just means structure. The second one is convergence to a maximally separated configuration, which is the Simplex ETF, which is the maximally separated structure and equiangular and equinorm structure within a space where the number of vectors is smaller than the dimension of the space itself. And given this audience, I feel like I should bring up a technical point here, which is the traditional ETF, which is what Dustin has spent a lot of time studying, is within a setting where the dimension, you have more vectors than you have dimensions of space. And because of this, the definition of the frame is that, one definition is that the smallest eigenvalue of the vectors of the frame is greater than 0, and then a frame is the upper one is bounded. That means it's full rank, right? It spans the space. Now in the deepnet setting, we're very much in a different setting, which is the dimension of the space is much larger than the number of vectors in this space, the number of classes you have. And what we felt was the best generalization or the most appropriate generalization of the equiangular tight frame in this context is just to retain the equiangular, retain even an equinorm condition, but not retain the spanning condition. And this, in some sense, if you restrict to just the span of the vectors, you'll see that within that subspace, it is in fact this tight frame that we talk about here. So we're retaining the geometry, and that's why we defined it this way. But given this audience, I feel like I should explain. And of course, there's something, the next property is self-duality, which is the means, which is the means of the activations, and the classifiers, which is the linear dual vector for what it's worth, multiplying them to give us this score, will be converged to each other, which is, again, intuitive, because we want the highest score for the, to get the highest score, we want the vector that's literally the same in some sense. So the means and the classifiers will converge to each other. Here we see the vectors kind of aligning. So one of these colors is the classifier, one is the means, and they eventually become the same thing. And by the way, this is not a cute graphic we just randomly generated. This is actually done using a dimensionally reduced version of training the VGG13 network on the CFAR10 data set. So this is actually a real data animation. And finally, so here's the first 3 neural collapse properties. And what happens under these properties, which we thought was so important that it deserves to be on equal footing in some sense with the other phenomena, is when you have 0 within class, when you approach 0 within class covariance, when all the class means become equinorm and equally maximally separated, what you get is that the behavior of the classifier, so this argmax thing that used to be the argmax of the scores, is actually just the nearest neighbor to the class mean itself. We actually proved this theoretically in the paper. So instead of this, take a linear combination and then maximize, take the maximum of the score, instead you're just saying, look at the class means, because they're the same as the classifiers anyways, eventually, and take the index, take the class mean that's the closest, and this eventually converges to the same rule. And so we verified this, and this is pervasive. Even though we have all of those, we have 7 benchmark data sets, including ImageNet, and 3 different deepnet architectures. So we have VGG, ResNet, DenseNet. We see this phenomenon. This is the first one, which is the within class covariance multiplied by the between class covariance inverse, pseudo inverse, because we know exactly what its rank should be, which is it's a centered covariance matrix of the mean, so it has exactly C-1 dimensions. Multiply that, take the trace, divide by C for technical reasons. You'll see that the within class covariance is definitely shrinking relative to the mean size. And why do we rescale by the mean size? Because again, your classification performance is always relative to the classifiers and means. Like, this is the classic signal to noise ratio idea. And because of this, you really have to rescale everything to reframe everything in terms of the means and see how much noise, which is SW, the within class covariance you're getting. And you see that, and here, notice that the y-axis is on log scale here. Throughout training, this within class covariance is very much shrinking compared to your signal, which is your means, across this 3×7 combination. And the next one is equinormness. So we take here, it's standard deviation. Again, we have to rescale, which is by the average. So we take the norms of the means. So the C different means, we take their norms, and we calculate the standard deviation of those norms divided by the average of those norms. And again, you see that they're effectively approaching 0. which means that all of these norms and classifiers are becoming equal in the eyes of the data set, and their classifiers and means are becoming effectively equal length. And equiangularity, this is the maximal separation property I was talking about earlier, which is here again, we take the angles and then we take a standard deviation of them. And again, we see this convergence here. It's slower, but it is there. Like even in these parts where it looks flat, like if you just dig into the numbers, they are decreasing. And it's slow, especially say for ImageNet. But if you look in the literature, you'll see that deep learning is slow. Someone like derived like log and log rates for things like this. So this is expected. It's happening, but yes, it's slow, but it definitely is happening. And this is just the maximum. So it's equiangular before. This is kind of a strengthening of that, which is it's equiangular, but not only is it equiangular, it's approaching that ETF angle, which is 1 over C minus 1. And here, what we call the shifted covariance is just we take the angle and we shift it by what it should be, which is 1 over C minus 1. We take the absolute value. So what is the deviation from that ideal angle? And this really shows that it is, in fact, approaching an ETF, a simplex ETF in high dimensional space. And again, we see this drop. And finally, self-duality, which is the classifiers approach the means. Again, classifiers, means, take the transpose because they're dual matrices, subtract them, take the norm, and I see they are in fact converging to each other. And of course, finally, what we call the nearest class decision rule. So is the rule of multiplying features by this Cth class classifier, take the maximum score, is it the equivalent to just taking the nearest class center among the training class? And you'll see that the proportion where they deviate goes to 0 with training as well. So this just verifies the 4 properties I talked about earlier across 7 benchmark data sets and 3 deepnet networks. And from this, what we're trying to show that there really is some sort of order, some sort of regularity within even all these architectures, all this noise that's been sprung up by the deep learning wave. There is this simple geometric mathematical structure emerging if you just look at the last layer of the deepnet. And to kind of finally give motivation for why we would even think about this, because in some sense you can say, oh, but you're training past interpolation. You already reach 0 error. Like this is such a new thing that people just do, right? Like why? Like, is it really getting better? Because is there a point to training past interpolation? And the answer is yes. So, and okay, where am I? Here I am. So if you look, this is the point where you reach interpolation. And this is the point where you say, if you just say, I'm going to train to 350 epochs, 400 epochs, regardless, this is actually 350. You do see these percentage point improvements in the test out of sample data. There are some exceptions for this. For example, CFAR 100 DesNet does increase, but most of them, the test performance increase. And so training past interpolation to 0 loss does have performance benefits. And this has been observed, like this is a formalization by us, but this has been generally observed, which is you should train past interpolation, and that does give you benefits. And it also gives you benefits up to some outliers in terms of robustness. So what do we mean by robustness? It means when you inject noise in an image, right? An image is, say, of a stop sign. And say if you're a malicious party for self-driving cars, for example, you want to inject not noticeable noise into an image so that, say, instead of a stop sign, a car sees a green light. That's the idea of adversarial robustness. So here, this is a metric created using what's called the deepful metric, but we won't go into that here. But this measures how much noise, the magnitude of the noise, do you need before you can confuse the deepnet into a wrong decision. And you see that as you train more, and the red line is when you reach interpolation of the training data, you train even past the interpolation, your robustness towards noise does increase. It takes a larger magnitude of noise that you have to manually inject into the images before you can confuse the classifier. So there is a benefit to training past interpolation to zero loss in this sense as well. And again, why do we care about this regime? Because this is the regime where if you just push it to the extreme, the classifiers and the features reach the ETF configuration. And so now, as we get more technical, like just to remind on the notation, we see that we say the last classifier, we concatenate all the WCs into a matrix W. H, we denote H or HL because it's the layer right, if L is the number of layers in the network, HL is the layer right before you hit the final layer of the network, which is W. So this is the first 100 layers if your network is, say, 101 layers deep. And the theta is the parameters of the earlier 100 layers, for example. And if we must be fully technical, we could say H is a function of the input images, X, and the parameters theta in the early layers. And these first layers is called this transformation is actually called the feature engineering aspect of the deepnet. Usually the deepnet is divided into the linear classifier, which is W, and the feature engineering. That's one way to abstract the network. So what will we show? Now that we showed that this does happen, what we'll talk about a bit now is that it is in fact the preferred state. It makes sense. Theoretically, it's the preferred state you would want a good class of network to be in when you are doing the classification task. And this idea has actually predecessors in the traditional non-AI literature. For example, in Claude Shannon actually talked about something that's more or less this in his 1959 paper probability error for optimal codes for a Gaussian channel. And putting it in similar notation to us, what happens is that you have a transmitter, someone sending a signal who must design some code words, right? So you have 1 to C different signals you want to send to the person on the other end. And for each one, you design this code word which is mu-C. And you have what's called a Gaussian channel, which is in the process of sending this code word, right? You'll end up with Gaussian noise on the code word you send. And there's a decoder on the other end who applies this argmax linear rule, which is effectively the same rule a deepnet uses to decode it, which is which gamma did the sender intend to send. I'm gonna guess using this argmax rule here. And your job in finding these code words is to choose the best code word mu to send so that the job of the decoder is easiest. And usually there's this norm bound in the classical case on the size of the mus. And so this problem, you'll see now, like this, what is the optimal configuration of the means problem? It's very much similar to how can the network engineer features? What is the best way you would expect or want a network to engineer your features so that it makes the clearest classification, which is captured by this term here. So this idea is even precedented in the days of Shannon. And to in our case, so now is where we move past Shannon. So what was Shannon talking about in his 1959 paper? He gave some exact forms for when your code word can only be 1 or 2 dimensional, and he gave a bound for what the angles between code words must be in term as the size of the code word. So the dimension of the signal you're sending goes to infinity. So those are the limits and cases Shannon was looking at. In this case, we actually think in a different way, because we actually do have something that Shannon did not, which is we know from our experiments, or from, I guess, the deep net setting, which is eventually the signal just overwhelms the noise. So the noise, which is captured by sigma here, goes to 0. Right? So say you have this noise right here, and in the deep net case, this sigma actually does go to 0. So then the probability of error goes to 0. So what is actually the proper limiting ratio to look at? And the proper limiting ratio to look at to get these to be something constant that we can grasp and analyze is what's called the large deviations error component, which is you take the probability of error. So this is the decision made by the decoder, and this was the intention of the encoder, or the transmitter. And the probability of making this error times the sigma itself. And these both of these are going, because sigma is going to 0, one's getting larger, one's getting smaller. So they this is the right ratio to look at them in order to get a constant limit. And you take this limit as you go to infinity, and this will be something roughly constant. And then what you're asking is, okay, with each each encoding rule and each decoding classifier. So remember, encoding is what you use with the mu, and decoding is what you do with the W's and B's. So classifier and biases. What you want to maximize this coefficient, which is maximize in some sense the probability of making the right choice. Across all encoders you could use, W's you can use, and biases you could use. And our result in the original paper is that there's actually the lowest possible coefficient you can get in a classical bounded norm Shannon setting is this coefficient C over C minus 1 times 1/4. And this is exactly achieved when both the features and the classifier, so both the encoding and the decoding, is equal to the simplex equiangular tight frame, which is what an ETF becomes when the ambient space is equal or greater than the number of vectors. And this is up to rotation, which is why we have an orthogonal matrix U here. So up to rotation, this is in fact, if you just do the analysis, this is the optimal configuration. It takes some analysis, but really it's an intuitive result. So yes, again, this looks similar. But so before we were talking about Shannon. Now there's another way to justify theoretically the same result, which we're just trying to drive home that this is really expected, which is, again, you have these code words you want to create. And now say you have an adversary who can inject A in just the right way to confuse you. What is what is this? And of course, you're still decoding using the linear rule, right? And now the question is, you're injecting this A, which is bounded by epsilon. And the idea is the adversarial radius is what is the smallest noise you can inject before you can create an error on any of the features. What is the smallest noise you can inject? Because that kind of tells you, right, like what the worst, how robust it is. You want the smallest noise to be as large as possible. So you want to design your classifier and encoding so that your adversary has to use the biggest noise possible in order to confuse your decoding procedure. So you see this max min, so alpha is a min, the alpha star is a max, and this is this max min structure reminds you of some canonical game theoretic formulations, and that's correct because that's what you should be thinking of. Your adversary is trying to confuse you with a min, and you're trying to make it as hard as possible for them to confuse you with the max. So what is this adversarial noise radius, and how do you maximize it? And again, it turns out this is a work under preparation because we're still tweaking some of the details, which is the best radius under the bounded norm case is square root of c minus 1 times 1 over root 2. And again, this optimal adversarial radius is exactly achieved by the ETF structure of both the encoding code words and the decoding classifiers up to a rotation U. So now we're kind of revisiting our slogan, which is neural collapse is the preferred end state of every successful exercise in future engineering. I kind of drove home this point by showing these almost very similar looking examples from motivated by theory, and showed that yes, the ETF is the optimal code book in decoding in a C-1 dimensional affine space. Why C-1 dimensional? Because the global mean of these things really doesn't give you any information. It's their deviation from their collective mean that really gives you the signal. So it's, you have C vectors, but really you only have C-1 spread on those code words in both, and we justified this in both the adversarial noise and the Gaussian noise setting. And now from that perspective, there's, so the before was from an encoding perspective. There's a different perspective, which is given a set of fixed code words. Before we could design our code words, but given a fixed code words, what are the best possible decoders for them, right? Given a fixed set of features, what are the possible decoders? And in 1990, for classification using deep nets, well, not deep nets, but just general neural nets back at the time, there's this result by Webb and Lowe that gave explicit results, which is given fixed features, the optimal classifier and bias is actually, so no feature engineering means your code words or your features are fixed, are given by this closed form. And this is just done by taking the first order conditions of the loss under MSE loss. And what we can show using just a simple series of steps is that if you have no within class covariance, so if this term is 0, and if you know that your features are already in that maximally equiangular structure, so you can't change your features, but if your features come as the ETF structure, what you'll recover is again a classifier that's exactly the ETF as well. So if your data is the ETF, the best classifier is again the ETF. And this just captures the intuition of self-duality, which is the classifier will match the features. And then more modern, within the more modern landscape, there's this paper by Sudri et al. That says, okay, suppose you have fixed features, you're a high dimensional space, so these features are separable. Then in this case, given a separable data set, if you're maximizing now the real cross entropy loss that people use for classification, with gradient descent with sufficiently small step size, which is a classical enough assumption, and no bias term because you can always absorb the additive bias into W by concatenating a 1, right? Then what will happen is that the classifier will tend to a scaled version of the C-class SVM problem. So even though you're minimizing across entropy loss, the solution you get is actually a scaled version of just the SVM formulation, which is up to minimizing the norms, make sure that all of the difference between the classifiers for the corrected. So this is a feature. We want this score to be bigger than this score. So this is really the subtraction of two scores combined using linearity. And we want there to be a gap, visible gap, between the scores of two different, between the correct class and the incorrect class. So that's how you should be reading this. And this is that classical SVM problem. This is what machine learning actually minimizes nowadays, which is the cross entropy loss. And it shows that these two guys are equivalent if the data starts out separable, which in high dimensional space is a pretty reasonable assumption. And what we again showed is, given this, if you're just maximizing separation, if you're just maximizing the SVM problem even, if your within classical variance goes to 0, and if your data just ends up coming, so again, you're not engineering the data, although there's been a recent paper by these 5 authors that actually does show that even if you're engineering the features under the same max margin SVM formulation, you will again get the ETF structure as well. They haven't properly archived it yet, so I can't reference it, but it's true even if you don't take this out, basically. But under these assumptions, you will, actually you can take this guy out too, I think, based on their derivations. You will again get optimal classifiers if you use the classifier being the equiangular tight form. In our result, we assume the data comes as an ETF, but in a recent 2021 preprint that has not been formally preprinted yet by a different team, they show that even these two assumptions are not really needed. And of course, that was our results, but since we released this, there's been quite a few teams, Dustin being the first, who extended this to various settings. In particular, Dustin and I'm not sure if Parsha and Pi are here, but they really constructed, formalized the underlying intuition that we had, which is this feature engineering, which we assumed to be just how we minimized it within its ambient space. What is the optimal thing within our P, where the P is optimal space? And Dustin kind of came along and formalized this into what he calls the unconstrained features model, which means it captures the idea that feature engineering is so over-parameterized that we might as well assume that we can optimize classifiers and weights as if they're unconstrained. Or that's how people have been interpreting it. And based on this idea, there's all these concurrent works. So Dustin did it for MSE loss, right? And then now there's Lua and Steinerberger, who did a similar thing for cross entropy loss, although they weren't optimizing weights, they were directly optimizing the means. E and Wojtowski, they minimized cross entropy within the unit ball. This paper actually gives an interesting result, which is you also hear all these this hype about infinite width networks and neural candidate kernels. They actually showed a counterexample where you really do need depth and flexibility in engineering rather than width, because they actually showed that a counterexample where you can start with data and you can never get neural collapse no matter how wide you make your network. So neural collapse is very much a consequence of the over-parameterized feature engineering of the depth of networks rather than this alternative abstraction that people have been using, which is width. There's Ergen and Palanci, which convexified the network using this formulation where they just put all the values in the constraints, and using this, they actually went to a 2-layer abstraction. So they assumed the linear classifier layer, but they could go one more up, which is a batch norm layer, and showed that deep neural collapse appears there as well. So this is what happened in 2020. Things have continued to happen in 2021. So Poggio, Lau, and Bambursky. So these works are very connected, so I put them together. But in their work, they consider homogeneous networks, which is networks that that can be collectively scaled by a constant. So it can't have, say, an additive bias in any layer. But if you so a scaling on one layer could equivalently apply to another scaling on another layer. They show that in such networks, especially for the binary classification case, you would expect neural collapse. Fang, He, Long, and Su examined two things. They examined the imbalanced class case. So in all our analysis, we considered class to be examples per class in their training to be equal, but they thought, what happens when you have imbalances? Well, it turns out the angles shrink. And once they shrink enough, they become exactly the same. And they call this minority collapse, which is if you have a class with just minority training examples, eventually the vectors of the frame just collapse to each other. They don't shrink uniformly to be smaller and smaller. Eventually, they just snap. Zhu, Ding, Zhou et al. What they did was they showed that there are within Dustin, Partial, and Pai's unconstrained features model, there are no spurious local minima. All local minima are global minima, and all of them have neural collapse. And they do this using a matrix completion argument. And this is them, and they also run some experiments showing what happens if you don't use SGD, what if you use Atom BFGS. They experimentally demonstrate that they also see neural collapse there. And this new paper where we actually archived a new version today, where we say under the unconstrained features model, if you just consider a recalibrated frame where you always, I'm running out of battery. Let me plug my computer in. If you just reorient the coordinates in which you consider your features, you'll see that you can actually, within those coordinates, you can look at the singular values of the features as a differential equation there. Within that coordinate system, you can actually derive the closed form dynamics there. So people have really been working to expand this theory, and there's an unnamed preprint here because it hasn't been on archive yet, where they showed that under the Marx margin narrative, you do get collapse, which is what I talked about earlier. So to conclude, what we showed is that canonical deep nets datasets, despite all their variety, exhibit neural collapse. And this simple symmetric structure of NC1, NC2, NC3, NC4 happens in 3 canonical data sets and networks. And intuitively, we can theoretically understand it to be the neural collapse forcing the features and classifiers to this optimal configuration under the traditional adversarial noise setting, as well as the Gaussian noise setting. And within more machine learning context, you could also think of it as if your features does come as an ETF, the classifier would in fact match it, which is the idea behind the modern variant of Webb and Low and the extension of Sudri et al. And finally, we're quite happy that people have been thinking more about this, building and creating, following up, examining it in more settings, and it's a growing body of work, and we hope to get you interested as well. So that's all. And I'll be happy to chat more, answer some questions, but thank you for your time. Thank you for coming.
Great, thanks, XY. Be sure to smash that reaction icon to express your appreciation, and I'll stop the recording now for the question session.